Thank you so much. Hi, Nirupam Roy. Great talk. And from Ruan, I am going to talk about our work on how to sense physical systems better, and not only for larger cyber physical systems, but also for the tiny ones. And let me just start by saying that my clicker is not working. Let me start by saying that we have started to see the research flow in autonomous cyber physical systems, at least at the large scale, and not only for the vehicle at various different aspects and different form factors and different applications. But at the same time, there are a plethora of work that can only be done with very tiny, very small robotic systems, and dangerous work that human cannot do, some of the delicate work that, again, human is not the most efficient, various of applications where tiny cyber physical systems can step up and rescue. We have started seeing lots of work around this space that will enable tiny locomotive, small moving robot, cyber physical system that can interact, that can move and navigate in the space. But at this point, we are mostly focusing on how to make these robots move. But at the same time, we need to think about how this kind of robot can sense the environment, because for autonomy, it is almost inevitable to create a closed loop system that can sense the environment, take decisions, do compute on the same thing, on the same platform. When we try to do that with this evolving space of tiny robot, we see that our smaller counterpart does not have that much of resources, just like a bigger car that has 60 ampere hour of batteries, and only 25 milliampere hour of batteries are given to this tiny system. When we do the big breakdown of how much power or how much energy is given to the sensing part, let alone the moving robot and moving parts of the robot, we see only a fraction of that, only 30 milliwatts of power that can be budgeted to sensing the environment. And for that reason, now the sensor that we can use for this tiny robot has become almost comical, that it can only have a distance sensor, ultrasound, maybe only one microphone that can hear the environment, and that's all. But to be able to sense the environment, it needs to have the spatial understanding. But the 30 years of research in array sensing, localizations of sound, using sound as sonar to find the depth and all, those does not replicate well to the small, tiny platform. And that's where our research comes in. Our group is focusing on making a mark in this multidimensional optimization problem, where we want to develop a system that is accurate and scalable, at the same time is not power hungry, and we do not want to stick ourselves to have one-dimensional microphone recording or something very simplistic as depth sensor. So in interest of time, I will skim over two specific research that we are currently working on. One is, and both are focusing on making this tiny robot navigable in a complex space and making it autonomous, creating a system that can sense the environment and compute and take decisions on board. The first work is around perception of navigation, how a tiny robot that can sense the environment using acoustic signal. And the second one is how it can localize in the large space of in entire, say, New York City, how it can find these locations without spending too much of power or carrying a battery that looks like a power bank. So let me get started with the first one. We started with a very humble question: can we enable directional hearing in tiny robotic systems instead of using an array of microphones that is traditionally used. So directional hearing are popular, and the theory is established mostly based on the array of microphones. We have seen huge amount of energy, huge amount of research around this space that created huge, big, large arrays, and mostly dependent on the fact that how signals are delayed and received by individual microphone placed in a certain arrangement. While these large array of microphones are good for its original target application space, underwater, big vehicle navigation, it does not hold good when we try to put them into our target application space where the robotic and cyber physical systems are very small. And we want to have low power ambient computing where the environment is smart enough to understand the directionality of the sound and so on. To play in this constraint, when we are struggling to find simple directionality of the sound in a small system, if we take a look at the nature, they do it with ease. It's called a burn owl, and they have remarkable directionality sense with only one pair of microphone, if you will, in both of the ears, but it has an interesting structure of the skull that sense the sound when it actually percolates through that skull. It creates a unique impulse response, and its neural network, the real neural network, learns that directionality and can find very pinpointed, very directional angles of arrival for sound. On the other hand, we have other animals like small cricket. They can also find they survive by finding the direction of arrival of sound of the predator. And the way it works is very similar. The sound interacts with the structure, and they have learned the directionality from the received signal with some weird and different impulse response before it gets to their hearing system. So we ask the question that can we break away from the traditional way of having an array and the way we are taught in the class that direction of arrival can only be found if we know the diversity of the phases across multiple positional recording, right? And probably these examples gives us a hint that directionality or the spatiality of the sound can be learned as well. It does not need to be analytically found out using an array of microphones or so on. Okay. With that idea, we tried to learn the directionality of the sound, but the problem is we could budget only one microphone. Can we do it with only one microphone, which does not have any diversity in the spatial direction? So what we did, we created a 3D printed measurement that can be simply thought of as a cover on that one microphone, but with the different patterns of holes that create the diffraction of the sound when it enters through the microphone. I think it's dead. It's dead. I'm talking about the power problem and here but I think I'm loud enough for everyone to hear.
No, we want to hear this.
Okay. So the way we did it, we created a 3D printed metamaterial. The only purpose of this metamaterial is to create an unique signature for different directions. And if we can do that, it can create a unique spectrum depending on which angle the sound is coming from. And the simple approach to that, it will diffract when we know that if there is a small opening in that metamaterial, sound will enter, it will diffract, it will create a multipath environment inside that. And if we can design this metamaterial well, And I'm calling it metamaterial, but essentially it is a cap with some interesting holes pattern on different sides. Right? And if we can do that, we can find different signature. We can learn that signature of that metamaterial in the lab, and we can use it as a directional signature, directionality sensor, making this small, tiny robot, tiny platform to understand direction of arrival using a small 1 microphone in a low power system. So that's what we did. We created this kind of 3D printed system. But here I'm skimming, I'm rushing a little bit over here. Multiple different problems are involved here. If you train the system in your lab and take it outside, try to make it work in the wild, the multipath environment is going to be different. The environment is going to create a different impulse response, and that's not going to work. So to avoid that, we added one other microphone, but not for an array. It is just a reference microphone that will try to sense the ambient signal, and it will also learn the difference between the impulse responses between these two, and we have shown a way to cancel this out in real-world experiments. So the approach boils down to, first we have a desired directionality, desired pattern in frequency per angle of arrival. We have understood, we have learned the physics of that to be able to create a metamaterial or the structure of that cap that works best for our angle of arrival estimations. And once we have this optimal structure, we use it to collect data, train in the lab, and test it in the wild, so that it will create different angular pattern for different frequencies, and later it can simply replace an array of microphone that will need at least 9 different elements. It will take 100 times less energy, 9 times smaller than that, and works better than this kind of array. So that was one problem we solved, where robots can have better understanding about the acoustic environment, learning the directionality of the sound. But the next problem that we touch upon is, now can we enable similar 1 microphone, 1 speaker system have a sonar-like depth imaging for machines? So traditionally, tiny robots use something called depth sensor, ultrasound sensor. One sound goes out, it hits the object, comes back, and we calculate the time difference to find one measurement of the distance at which the sensor is looking at. But can we do something better, that we can have a spatial depth map, cross-sectional depth map, using only 1 microphone, 1 speaker combination, that can make these tiny devices behave like an autonomous car that is constantly checking out its depth map in 360 degree using LiDAR or so. Can we do the similar thing, sophisticated environment sensing, using a tiny robot? The way these direct LiDAR systems work, or any array-based systems work, it will steer the beam at one direction at a time. Basically, it will scan the environment, send the signal, wait for the reflections to find the depth of or locations of that object. But with 1 microphone and 1 sensor, we do not have the capability to steer the beam at one direction at a time. Whatever reflects back comes as a combination from all directions. It's really hard to unravel those reflections once they are mixed up in the one-point receiver. Okay? But could we color different directions using different codes, so that when the reflections come back, we have a way to tell that which directions the signals are coming from, and later that will again combine together, but we can have a reverse problem, traditional reverse problem, just based on the code that is being reflected, given that if we can color the direction while shining the environment with one speaker. Right? And how can we have this directional code sent out at different directions? One can say that use a speaker array instead of microphone array, use a speaker array, same idea, focus the signal in one direction, and it will be done. At each direction, we can have a specific complex code embedded into the signal that should solve the problem. But again, sensors array are very power hungry. We cannot hope to have multiple speakers on a tiny insect scale robot. Again, we can do something with metamaterial, and in this case, we are covering the speaker with a metamaterial that has some unique channels to propagate the signal when it's passing through that metamaterial. It will have unique directional gain depending on which channel it has passed through. That will create some combinations of impulse response of the projected signal for each voxel in the region of interest. And to do so, we again run some optimizations to find out what is the best way to have this directional code using this metamaterial. We 3D printed this, and we tested that system with our with a navigation problem that we have. You can see that with and without this cap, the metamaterial cap, the spatial diversity of the signal is much less. But after that, we can have unique spatial diversity. Almost every voxel in that the region in front of the sensor can have an unique combinations later from the reflections. We can use this to unravel those and find out the distance and location of the object in front of this. Here is a couple of evaluation results where we have the sensor and we have one object in front of this, and the results are showing from the top view. You can see that it can identify the distance of the object where it's reflecting from. At the same time, the separation between two objects are also detected. So it may look like way too less resolution, but remember that it's less than 5 milliwatts of power, and it can range the region in front of the sensor with that. Now, the question is the structural way to add diversity, and you use that structural diversity to find the directional information from signal. Is this only applicable to acoustic? The natural question is, if we could do it with radio frequencies, RF, maybe we can have larger range. We can solve problems of localizations and all if we can apply the same idea in radio frequencies. So we tried that out too, and it is easier to change the structure of an antenna, which can be thought of as combinations of metallic patch, and we have some of the switches that is turning on and off in the real time, which means that we have a sort of metamaterial that can change its shape over time. Now, we can switch these switches or change the metamaterial impulse response at a rate of nanoseconds. And when it is receiving the signal, we can change the directional gain of that antenna, creating, again, an unique pattern. And the only problem left to us is to find out the directionality by mapping it, the code or directional gain that it has received. This is a crude antenna that we developed in our lab, but we are working with the developer to have a more sophisticated version of this one. So this part was about how to use a passive structure to enable spatial sensing with very low power, and not only low power, in small form factor as well. From the array theory, we know that to achieve a certain directional resolution, the array either needs to be placed far away, and it also has the limitations of how far two elements can be. Everything boils down to the point that we cannot make an array small enough to fit into a small platform, let alone a small hearable device or so. But with this metamaterial, now we do not need a wide array. Even for lower frequency that has a large wavelength, we can pack that array into a small system, almost similar to a wearable device in ear. It actually attracts lots of attention from the community, and students got lots of awards. I'll be happy to talk about that, and connect you to the student if you are interested in that. Let me quickly jump to the second part of our talk, which is passive self-localization. The point is when a small tiny drone is flying around in a larger area, can that drone localize itself, self-localization, just like a GPS, right? And the problem is similar in tiny robot, and as well as packet delivery and any localization you can think of. And in localization community, it is actually common adage to say that tracking a box is much difficult than tracking a large container. The reason is that if you are tracking a large container, you'll simply put a GPS tracker on it. You can afford battery power to run that GPS, which is very power hungry, and it also have a communication system to return back the learned GPS location. And the way it works is inherently power hungry because it will try to decode the signal from all the visible satellite, and then it will do some triangulation to find its location. Okay? But our dream tracker or dream passive localization system is just like a sticker, which is just like an RFID system that gives us GPS-like accuracy, but runs with a fraction of the power that's required for this. And also, at the same time, we want the battery to last for a long time because this is the applications we put together for tracking a box at the very micro level in urban areas. The same idea is applicable to localizations of a self-drone or cyber-physical system. The idea is that we do not really need the satellite to localize, to triangulate and localize a tiny chip, because we already have the infrastructure, which is cellular infrastructure that's already built in. Almost over 90% of the world is already covered under LTE or cellular power. In the past, people tried to map the power of cellular towers in certain regions, but that is grossly erroneous, and it doesn't work very well with a smaller system. So the idea that we are trying to explore here is that each of the cell towers, in LTE, there are plenty of cell towers. With 5G, there are going to be more. And each of the cell tower will have a unique pattern of signal when it's going out. It's called the code connected to the unique location and the ID of the cell tower. If we can decode those cell tower ID, the presence of the unique combinations of those cell tower ID can be mapped to the certain locations of that chip. But if we could decode everything, which means that we are making another smartphone that is trying to find its locations from decoding multiple cell tower signals. That's certainly not going to work in a tiny chip. So we use a trick in the reception where before receiving the signal, we're passing it through a nonlinear channel, which means the 3 gigahertz spectrum of LTE will be folded down to 20 megahertz of spectrum. And now the challenge is to find the unique codes of the cell tower from this nonlinear transform spectrum, 20 megahertz spectrum. And neural network loves this kind of problem. We have shown that the code has unique properties that is maintained even when it is folded through the nonlinear transformation. And if we can do it well, we can not only find the power of unique cell tower signal, we can also find the distance or separations in time of individual cell tower code. We created a tiny flexible chip with the antenna that we need to localize, self-localize it on that small chip by discerning the number of cell tower it can see at any particular location. And we drove around with that chip in DC area, rural and urban areas. You can see the result on the right-hand side. In the rural area, the cell towers are sparser. That's why the accuracy goes down. But with 5G and the latest version of our code, that can find the timing of each of the cell tower signals very accurately. That will improve the accuracy in the rural areas as well. Now, the other fold of this problem is not only finding the locations, can we track a swarm of tiny agents in a large, vast area like a city or larger than that? So we model the problem as a graph theoretic problem that is trying to find opportunistically talk to other agents and try to create an evolving map over time. With the simulations, we have shown that with 100,000 nodes, we can track the locations, we can map individual locations in form of a graph in real time. Interesting thing about cellular signal is that it passes through everything, passes through wall. You can open up your phone and you can still see the signal, which means that the tiny tag can be tracked within a building as well. So that's all that I wanted to talk about from the technical side. Here is our lab website, icosmos.cs.umd.edu. Visit this website for more information about that or send me an email to learn more about it. So thank you so much. I'll stop here.
Very interesting talk. Okay, so let me ask you some questions. You do know that analytically we understand how the cricket does it, okay? We do know how the cricket does it analytically, right? There are old studies that we use with Sama here to show that all you need is a quadrant, like a four-direction directivity, and that's what the cricket does. But the processing is non-linear. It's not linear, and it does not depend so much on the head for the cricket. Yeah, these are old papers on the cricket. Okay, I don't know if you have looked at them and.
That the way the neural processing is happening.
No. There's no machine learning, nothing. Okay, the question was, how come we do it with 2 ears, right? Why do we don't have an array? Okay, and partly is the structure of the head, but that's not all. The mistake that people are doing is that if you look at the classical array processing, it's linear, it's correlation processing. What Sama showed by using the tonotopic map of the brain and other things is that the actual processing is non-linear. And then actually, was the guy who was at Caltech who was doing the VLSI, he created a nonlinear processor and reproduced that if you do the nonlinear processing with 2 microphone, you can find big directivity. And that's why we studied the cricket then. So, and why I'm asking, the question is this then. You create this structure, which is wonderful, but does whatever structure they impose on the signal, is it robust with respect to noise in the environment when you get back? That's the question. Because we did similar things for smart surfaces, for 6G, with NEC. Yeah. You can exactly the same idea you imposed on coding on the waveform to try to create different things. But the key question was, can you show that this additional coding that translates into some characteristics of the wave is maintained on them when you come back? Otherwise, you cannot recognize it, right? And it has to be in a real environment, not in the lab. So the question is, and I'll stop here, have you done experiments where you take these wonderful structures you create and you create this special coding, either acoustically or other, and then show that in an actual realistic environment, they maintain themselves so you can detect them?
Nice comment. I mean, we should go back and actually open the paper and look at that. Thank you so much.
So, really great talk. How were you able to get the data layer back from the tags to infrastructure? Was this about the boxes knowing where they are, or is it about you knowing where the boxes are?
So the problem with the box tracking was location provenance, which means that the box will travel anywhere in the world. When they will come to the warehouse, they will collect the data and process that where it has been.
Okay, so this is just about the box knowing where it has been,
Right.
not about some other person knowing where the box is at a
Right. So
time.
it is as if it is storing all the information, and later it can be mapped back to the physical location.
Gotcha.
And it works straightforward with when we are using this as a GPS-like tracking locations on a drone, which can directly talk to the chip to find its location.
Thanks.